We are going to start with Dr. David Gutzler, who is a professor of meteorology and climatology at the University of New Mexico. His research is based on analysis of observations and climate models with the goals of understanding the causes of climate variability and change, and improving the skills and application of forecasts on seasonal and longer time scales. After Dr. Gutzler's presentation, which will last about 20 minutes, we will have a couple of additional speakers, and then following that we will take questions. So if you have questions, please wait till the end of the second presentation, and at that time we will unmute your phones. So I'm going to turn it over to Dr. Gutzler.
Thanks, Mike. I'll spend 20 or so minutes describing some research that I've done, most of which was done in collaboration with a grad student named Shailene Chavarria, and so I want to acknowledge her. She now works for USGS at the New Mexico Water Science Center. Both of our presentations here today will be focused on processes that modulate stream flow up in the headwaters of the Rio Grande. And so I'll start just by looking at this map that's in the upper left of the slide on the screen. The large-scale context here is that the Rio Grande starts in southern Colorado, has its headwaters there, and flows southward through the black and gray regions on that map. The black regions are where the flow is generally snowmelt dominated, and that snowmelt runoff signature extends down to southern New Mexico, where there's a big reservoir that essentially resets the flow, because the outflow from that reservoir, called Elephant Butte, is very highly regulated and serves the needs of users downstream. We'll be focused in the upper part of this basin, where if I blow that up and add a map looking just at the region in southern Colorado, these presentations today will be focused on processes happening up there, and in particular I'll be talking about flow at a gauge called Del Norte on the upper Rio Grande, which, as you can see from the map, is located where the Rio Grande opens up into the San Luis Valley. So up above the Del Norte gauge, the flows are very heavily snowmelt driven, and there's little enough human activity in the form of dams and diversions that we can use the gauged flows and interpret them in terms of natural processes. And we'll be hearing more about snowpack processes from David Clow in a few minutes, and his colleagues. So my conclusions are going to be that I'll try to show you that in this region, temperature has been rising and snowpack has been decreasing at a pretty rapid clip for several decades already. However, the scientific conundrum here is that as that happens, we see only very modest observed long-term trends in streamflow volume. In fact, they're not statistically significant, and I will try to show you that we think that that's happening as a consequence of snow turning to rain in combination with natural variability of precipitation on decadal time scales. And we combine that, and I'll say a few words about point 3, which is relating how these changes in hydrologic processes up in the headwaters have been working to degrade the quality of seasonal water supply outlooks over the last several decades. Sorry. Okay, to motivate this, I just wanted to show you very quickly what climate models are forecasting for this region, which is part of the reason we're so interested in what's going on up in the headwaters. And that's simply that all climate models project rapid temperature increase over the course of the 21st century. And a consequence of that is that a whole family of different kinds of streamflow models, surface hydrology models, have projected that streamflow in the upper Rio Grande should diminish overall, as shown by this hydrograph on the right, and that the snowmelt runoff peak, which is currently here in May, shown by the black line, should push weeks earlier to an earlier peak as the snow that remains melts earlier. So it's not shown explicitly on this figure, but the big changes we see both across the Southwest and the major river basins such as the Colorado and the Rio Grande, and in this hydrograph on the right, are due to diminished and earlier snowmelt runoff. Those are based on models. So what I will talk about here are observations. And then first, by way of background about snowpack, here's a slide showing what we see in the mountains of southern Colorado for snow accumulation and ablation in the historical record. And the point of this, of these two graphs here, is to show you that the average snow water equivalent curve over the course of a water year, shown in black, it's the same curve in both panels, tends to peak right about April 1st, and that is the canonical peak snowmelt date in the southern Rocky Mountains. But in addition to an average peak on April 1st, what we see is that if we average a bunch of above average snowpack years, so that is to say, the curve on the right shows a bunch of years that all have above average snow water equivalent on April 1st. And the curve on the right shows a bunch of years where there was below average snow on April 1st. And the point is to show that almost all the above average years exhibit above average snow accumulation even well before April 1st. So we get predictive value even early in the calendar year by looking at the observed snowpack in the southern Rocky Mountains. And I should say that these curves are all based on a single SNOTEL site, so the confidence we have in above average snowpack is increased if we're actually looking at an average of sites. On the right, we see that almost all the years in which there was below average snow on April 1st also exhibited below average snow well before that date. And so once again, we get predictive value for diminished snowpack even early in the calendar year. And that's where most of our snowmelt runoff prediction skill comes from, is looking months in advance of the snowmelt runoff season at the accumulation of snowpack. So if we look at climate change in the upper Rio Grande Basin, we can show that in this slide, which shows observed annual average temperature and precipitation in the Rio Grande headwaters, which turns out to be a climate division recognized by NOAA. So these are climate divisional averages of cooperative observer weather stations in the Rio Grande headwaters region. And what we see is that the temperature curve on the top has been going up with considerable interannual variability, but in fact, in these glorious native units of degrees Fahrenheit and inches, there's been about a 3-degree increase in recent decades, which actually turns out to be pretty similar to a mid-range climate change projection for the 20th century in terms of the rate of change. So really what climate projections are telling us is that it's a reasonable expectation for a continuation of what we've already seen over the past 40 years or so to occur for the rest of the century. There's nothing particularly extraordinary about the projected rate of increase. It's just a continuation of what we've already seen in this basin. On the other hand, the precipitation curve at the bottom shows wet decades and dry decades, but there really is no observed trend in the data in precipitation in the upper Rio Grande. But then if we look at snowpack, we see a curve that is more similar in character to the temperature curve. So Shailene Chavarria put together the curve in the upper right, which is based on relatively low elevation snow course sites as opposed to SNOTEL sites, which are used more frequently these days. The advantage of the snow course data are that they go farther back in time, and so if we take an average of snow course sites shown by the yellow dots on the map to the left, and average them together using a weighted average based on an eigenanalysis, we get the curve in the upper right, which actually shows that, again, with lots of interannual variability, that overall there's a 25% decrease over the period of record in April 1st snowpack if we just fit a straight line to those data. So that's a very significant decrease. Again, with lots of interannual variability. The curves in the lower right simply serve to try to convince us that the snow course data are reproducing interannual variability reasonably in more recent data compared to the SNOTEL sites. And as we would expect, the SNOTEL sites given by the dashed lines show higher absolute values of snowpack because they're generally located at higher elevation. So what we see in the climate record is, over the past half century or so, is a rapid increase in temperature, a corresponding decrease in snowpack, and very little trend at all in total precipitation. So what we see as a result of all that is very little change over the period of record in the discharge at the Del Norte gauge. So in the lower right, we see a time series of total volumetric flow. There actually is a very small decrease in that time series. It does not pass standard statistical significance tests. So in comparison to the rather dramatic decreases in stream flow that climate models project, what we do not see in the data, even during a period of temperature increase and snowpack decrease, is a corresponding big decrease in water year discharge. And that is one of the things we'd like to try to understand. However, if we parse the annual cycle, parse the total flow into an annual cycle, we can look at the early decades and later decades of our period of record in the upper left. And we see hydrographs at the Del Norte gauge that show a change in the pattern, the monthly delivery of stream flow past the gauge that looks qualitatively somewhat like the projected hydrograph changes coming out of climate models, in the sense that we see a very large decrease in stream flow in the summer months of June and July. So if I just compare the absolute value of flow in June and July in the early and later years, I get a change that's shown in the lower left of these bar chart curves here. I see a modest increase in the spring months of March and May, and it's that increase in the spring month flows that's compensating for the large decrease in summer flows during this period of time. So, but if I compare the early decades and the late decades, what I see is a flattened hydrograph and increased variability. So there is some similarity in what we might expect from climate change models simulating the effects of a warmer climate, but we don't see the absolute decrease in total flow, at least not yet. Part of the answer here, I think, has to do with the decadal variability of precipitation. So if we say there's no long-term change in total precipitation, there are some changes that we see if we look more carefully at winter and early spring months, that's the green curve on this plot, versus the later months, which are the months after peak snow from April through July. And what we see is that there is a lot of decadal variability in both of these curves. And the decadal variability, that is the general tendency for low precipitation values back in the 50s, with several wet decades in the 80s and 90s, and then more recent drought years, looks the same in both curves, which is to say that those decadal fluctuations seem to be similar across the seasonal cycle. But on an individual yearly basis, there's no correlation between winter and spring precipitation. So what that tells us is that there may be some annual coherence to the decadal variability of precipitation, but on an annual basis, if we're trying to make a stream flow projection, then how much rain is falling into the system late in the spring and in the summer is totally uncorrelated with winter precipitation associated with snowpack, and that helps us, that degrades the quality of an annual water supply outlook over this period of record. And to make matters worse, from that perspective, if we actually look at the variability of these curves, the interannual variability of the orange curve, that's the spring precipitation, is increasing by a lot, actually. In recent decades, it's up about 50% over what it was in the early decades of this period of record. And that, too, is going to make annual water supply outlooks harder in this period of time when snowpack is decreasing. Okay, to try to put all this together, I find it useful to think simply. That's how my brain works. So here's how I think about the water cycle using this cartoon. And so if what we are thinking about is what determines the flow of water in this river past the red square downstream here, and that's affected by a number of things. If we start up at the top, we have snow which accumulates into snowpack, and that's the predictable part of all this because we can actually see the snowpack accumulate, and we can look at the effects of that snowpack on downstream flow using something like a runoff ratio, which is just the ratio of downstream flow divided by either precipitation or snowpack. In addition, we have rainfall that falls into this system, both in the winter increasingly as temperatures warm up and later in the spring. And that rain is a source of uncertainty now, and that uncertainty is going to increase as the snow decreases and turns to rain. We may have some seasonal predictability of large-scale rain if we start incorporating seasonal precipitation forecasts into an annual water supply outlook, but we need to do an awful lot more work to make that happen. And then finally, I haven't talked about this too much in this presentation, but there's convective rain that also falls in this system in the summer, for which we have essentially zero seasonal predictability and for which our long-term climate change projections also don't provide us with too much guidance. So if we want to understand how this system works with an eye toward long-term projections or year-to-year predictions, we need to think about snowpack as the signal, and the snowpack is decreasing, and rainfall as the noise, and the relative importance of the rainfall has been increasing in recent decades relative to the snowpack. I can try to quantify that by looking at this set of runoff ratios that are calculated in several different ways. So there's a lot here, and I want to just kind of fly through the key parts. So if we look at these two scatter plots on the left, the x-axis here is April 1st snowpack. Each dot represents a year, and the y-axis represents the April through July discharge at Del Norte. And what we see in the upper left is about the best possible case for making a seasonal forecast or for understanding how much water is going to flow down the river based on snowpack, because the dots provide a real close fit to that just linear regression there. So if we know snowpack on April 1st in the upper left, then we can make a very skillful estimate of how much water is going to flow down the river between April and July. Then what happened over the past few decades is the climate warmed up. So the first thing you see is that the right-hand part of this graph is chopped off because we no longer have those high snowpack years that we had in the early decades. And the fit to this scatter plot is considerably worse in recent decades. So the R-squared value, that is, goes down by a lot relative to the earlier years, which tells us that the simplest possible statistical forecast that we could make, in which we predict April through July discharge based on April 1st snowpack, is just going to be a lot worse. There's another feature of this, these two graphs, and that is that the slope of the line is shallower in the lower plot, which tells us that the sensitivity of runoff to, in this case, April 1st snowpack is now less, and I would argue that is what we would expect to happen in a period of time when snowpack is decreased relative to the amount of rain, which, remember, is not exhibiting a, the total precip is not exhibiting any downward decline. And so the sensitivity of our forecast is getting worse. And I could make pretty much the same argument using a more traditional runoff ratio based on winter precipitation. So I would say that the effects of warmer temperatures exhibited by these runoff ratios is already being seen in our attempts to make year-to-year forecasts based on snowpack. So to wrap things up, I hope we've shown that climate in this region is changing in ways that really should affect surface water resources over the long term, as climate models would project. So we see temperature going up and we see snowpack going down. However, we don't see significant long-term trends yet in precipitation or stream flow. I think the reason for that is that over recent decades, the effects of springtime precipitation, which have been both higher and more variable than in recent decades, have been masking the effects of long-term changes in temperature and snowpack, but that's a working hypothesis for our ongoing research. So what we see in the data is that warmer temperatures have diminished the snowpack, and precipitation other than snowpack has varied a lot, which has decreased both prediction skill and predictability, and I make a distinction between those two terms, but you can ask me about the distinction later. We've shown a complicated set of runoff ratios that show somewhat different things if I base them on snowpack or precipitation. And we're doing an awful lot of follow-up research right now to try to understand those scatter plots more thoroughly than we do now, and to incorporate the effects of temperature explicitly on them. And in order to understand how this hydrologic system works, we're going to have to distinguish snowpack itself from the spring and summer rainfall variability. In other words, we see the effects of long-term climate change and decadal climate variability all mixed up in ways that are going to be very important to tease apart if we want to increase our understanding of the system and increase our prediction skill on annual timescales. And I'll wrap up there.
Thanks, Dave. Danielle, if you go ahead and switch us back over to Dave Clow. So let me introduce Dave Clow and his team. Dave Clow is a research hydrologist at the USGS in Denver, Colorado, where he began his career with the USGS in 1990. Dave has been working in the field of snow hydrology since 1984. On his team are also Colin Penn and Graham Sexton, both of whom serve as hydrologists there at the USGS office in Denver. Colin started as a seasonal hydrotech in 2010, and Graham's research focuses on seasonal snow hydrology and the importance of snow processes to water budgets, water availability, and water quality in the western U.S. So, David, take it away.
Hello, can you hear me? This is Dave.
Yes. We can hear you now.
Okay, fabulous. Okay, So I'm going to start off our presentation with kind of just a simple overview of runoff, our water supply outlook, forecasts, and errors associated with those. Dave Gutzler gave a very nice presentation on the influence of climate variability and change on snowpack and on stream flow. Our presentation is going to focus a little bit more on the effects of disturbance on snowpack and stream flow and water supply. Our project objectives are to identify potential sources of error in existing forecast models. Secondly, to improve our understanding of snowpack dynamics within the watershed, and Graham will talk about that. And then also to develop a new hydrologic model for the basin to aid in forecasting, and Colin will present those results. Okay, the Rio Grande headwaters are shown here. The pink box in the upper left of the map shows the study area. And here is a simple map showing the outline of the watershed in pink. Gauges run by the Colorado Department of Water Resources are shown in green. And blue shows the some of the HRUs, the hydrologic response units. Here's just a map showing land cover variability in the watershed. There's a lot of evergreen, or at least there used to be a lot of evergreen forest. I'll get to that more in a moment. There's a lot of terrain above tree line as well, so a lot of alpine zone. One of the questions we pose are, how have land cover changes within the study area impacted runoff forecasting performance? And so what we're getting at there are, what are the effects of disturbance, especially on runoff forecast errors? Here's a simple plot showing the, first of all, the seasonal accumulation of snowpack through the year, starting in October. That's the light blue line. And generally, the peak sweep occurs sometime in April, and then the snow starts to melt, and that's when stream flow starts to come up, and that's shown by the dark blue line. So the stream flow responds very directly to snowmelt. Snowmelt is the driving hydrologic force in the watershed, at least in the upper part of the watershed. So the NRCS provides water supply outlooks starting January 1, and then they do it again on a monthly basis through the springtime. And that is these arrows that are popping up show the timing of the water supply outlook forecasts. And you can see that the snow continues to accumulate through the springtime, and as you might expect, it becomes a little bit easier. We have higher predictive skill in the water supply outlook forecasts as we move through the springtime. So there's March and April, and this plot shows runoff errors by month, and it starts in 1990 and goes through 2015. These are the NRCS water supply outlooks. And we're showing the percent error in the water supply outlooks for each year and by month. And the next slide, I'm going to zoom in on 2002 so you can see things a little more clearly. And what you can see is that the percent error, if we look at the column over on the far left, you can see there's a lot of error in the water supply outlook forecast in January. The error goes down in February, and then again in March, and then there's April, May, and June. April 1st is typically, that's sort of the standard that is commonly used for making important decisions about water supply for the year. And this slide indicates how the errors change through the course of the springtime. So in January, there's a Nash, so the Nash set cliff is a measure of model accuracy. and the Nash-Sutcliffe index varies from -1 to +1. A value of 1 indicates perfect skill in predicting something. A value of 0 represents no skill. And you can see in January, the Nash-Sutcliffe for this group of years is about 0.31. So 0.31 indicates very moderate skill in predicting water supply for the year. Nash-Sutcliffe improves to 0.4 by April 1st, and then when we get to June, it's 0.74. So that makes sense because by that time, most of the precip has already fallen for the springtime. And so really, we should have very good skill by the time that has happened. But in April, our Nash-Sutcliffe is really is only 0.4, so it's not that high. This plot shows variability in the water supply outlook errors from 1990 through 2014 based on April 1 snow water equivalent. And this is for the Rio Grande above Del Norte, which is the same gauge that Dave Gutzler used in his study. Values that are above 0, this horizontal line represents 0. Values that are above 0 represent years where the predicted value for water supply was greater than what actually happened. And the inverse applies to values below the 0 line. You can see there's a lot of variability in the error. Some years there was a large negative bias, and in other years, like 2002, the forecast was way above what actually happened. So then one of the next questions is, what's controlling those, what's influencing those errors? Why is it so good some years, and why is it so bad in other years? Well, bark beetles have really impacted forests in Colorado, and this plot shows the timing of the mountain pine beetle and of the spruce beetle in Colorado forests. And so the mountain pine beetle peaked in around the late 2000s, but the spruce beetle has continued to impact forests in Colorado, and this plot indicates that it peaked in about 2004. Now, in the Rio Grande Basin, the upper Rio Grande, this map shows areas that have been impacted by the spruce beetle in pink, and the intensity is indicated by the darkness of the pink color. The plot on the bottom shows cumulative bark beetle impacts starting in 1999 and going through 2015. And there was a rapid spread in the mid-2000s, especially 2005 through about 2010 or 11. The bark beetle impacted about 31% of the Rio Grande headwaters. So here we've overlaid the bark beetle cumulative impacts on top of the errors in the water supply outlooks. And as you can see, the bark beetle, the timing of the bark beetle impacts, we're not really seeing a big influence on the water supply outlook errors. What about fire? So there was a large fire in the watershed in 2013, the West Fork Papoose fire, and it burned 81,000 acres, some of it fairly intensely. If we add that to our plot of the water supply errors, we can see that starting in 2013, when the fire happened, the water supply outlooks started to, the predictions were less than what was observed. In other words, we were getting more stream flow than was predicted by the regression equations that the NRCS uses. So with that, I'm going to turn it over to Graham, and he is going to talk about snowpack dynamics and how disturbance might influence that.
All right, thanks, Dave. Yeah, so as a part of this study, we're looking at snowpack processes and trying to see if we can use a combination of field-based observations as well as modeling techniques to potentially improve snow estimates for the basin. So as a part of our field-based activities, we installed 3 enhanced meteorological stations within the basin to collect some auxiliary data, things like relative humidity and wind speed and radiation, variables that are really important for snow evolution but aren't traditionally collected at things like SNOTEL stations. In addition to these meteorological stations, we've collected a variety of manual field-based observations of the snowpack. And particularly over the past few years is when we've been collecting this manual data. And so really we've kind of been collecting this information as a way to try to aid in our modeling effort. So we've developed a spatially distributed snow model for the Upper Rio Grande Basin. And, with the ultimate goal of, can this distributed model give us a better idea of spatially distributed snow estimates for the basin? And more specifically, we have kind of a few more targeted questions, such as, how representative are the SNOTEL stations of basin-wide snow accumulation and snow water resources? And this is kind of it's been a big question for a long time. It's, how should we be relying on these point measurements to represent snow across the entire basin area? This plot on the bottom highlights a few of our manual snow surveys that we collected around 3 different SNOTEL gauges in the basin. And so the blue SNOTEL snow water equivalent is shown for 2 different years, and it's compared to the historic average in red. So these water year 2016 and water year 2017 were fairly close to average years compared to the historic average. But the blue squares on these plots actually represent the average of our manual measurements that were collected pretty much in, a couple square kilometers around these stations. So this is, pretty focused specifically around these gauges, and we can see there's some pretty big discrepancies where, the snow we're measuring around the gauges, mostly within forested areas, is considerably less than, what this SNOTEL snow pillow is showing. So, in addition to trying to understand, how representative these SNOTEL stations are, we're really, trying to see, can this spatially distributed snow model be used to aid in runoff forecasting? So to give a real quick overview of the snow model that we've developed, it's called Snow Model. It's a spatially distributed process-based snow evolution model. So this little figure down here kind of is a nice representation of physically based snow models. So essentially they're run on a grid, and you can sort of specify, how fine or coarse resolution this grid is, but it uses a combination of elevation, land cover, and then meteorological forcing data. And for every grid in your domain, it essentially calculates the energy balance throughout the season. And this snow model is particularly important because it represents processes that are important in alpine environments, such as blowing snow, and also in forested environments, such as canopy interception and canopy sublimation. And these things are really important, especially if we're wanting to consider how forest disturbances, which are very widespread in this basin, may be influencing snowpack dynamics. So this is a few graphs just highlighting some of the model output for some of our preliminary snow modeling we've done. And really kind of just, this is basically biweekly plots throughout the snowmelt season. So this first plot in the top left represents April 1st, and then it goes all the way through July 15th. And so we have three different variables here. This plot on the far left is cumulative precipitation. The plot in the middle is snow water equivalent, and then the plot on the right represents runoff to the land surface. So that's, the combination of snowmelt and or rain precipitation falling onto the land surface. So we can see that there's a lot of variability that sort of jumps out in all three of these variables. And also, most of these forecasts are based on this April 1st date, and you see how, the spring precipitation, particularly in this year, was pretty important because we start to see, especially in this area near Wolf Creek Pass, starts to get a lot of spring precipitation, which can really, it's hard to see this graph here, but it does translate into pretty big increases in snow water equivalent at these higher elevations, and especially at the elevations that are above SNOTEL gauges and aren't always picked up by, what a SNOTEL is measuring. So this is just generally highlighting, a lot of the variability that we're trying to consider with this spatially explicit model. And so these plots represent essentially a comparison between what the average SNOTEL gauge is showing compared to, what our average of our modeled average for the entire Rio Grande headwaters is. So the red line on these graphs represents the modeled value that's averaged across the basin, and the dark blue dashed line represents the average of these five different SNOTEL gauges that are in the headwaters. So you can see this cumulative precipitation, our average model precipitation is actually fairly close across spatially compared to the average of these SNOTEL precipitation measurements. But when we look at snow water equivalent, we see a pretty huge discrepancy. And, we would expect that because these SNOTEL stations are located in these high elevation locations, really kind of set up as index sites that are meant to hold snow for a long time. But it's kind of important to note just sort of how the magnitude difference is pretty large, but also when we look at this snow melt season, the rate of melt is quite different when we look at a SNOTEL average melt rate versus a basin-wide average melt rate, where we have this tail that sort of, we end up eventually having more snow later in the spring than that SNOTEL average. And those are all things that, may be important to consider for a more accurate stream flow forecast. And certainly, stream flow forecasts aren't based on a water balance estimate. They're based on these linear correlations of SNOTEL and stream flow. So really one of the things we want to look at is how has this relation between the average SNOTEL snow measurements compared to the basin-wide SNOTEL or basin-wide modeled snow, how has that changed over time? And are there significant trends that we're finding in that relation? Lastly, we see this as in red, we have the modeled cumulative runoff to the land surface from snow model, and that's compared to cumulative stream flow measured at the Del Norte gauge. You see these are pretty highly correlated, but also there's a pretty large discrepancy between these two, and that has a lot to do with other hydrologic processes like evapotranspiration and change in storage that are really important to consider when making these forecasts. So, we're still kind of in the middle of this project, and work is still ongoing. So, kind of our next steps are to try to explicitly model these changes in forest disturbances, specifically by adjusting the leaf area index that the model uses through time based on measurements from satellite data. And then really trying to key in on, what are the changes between SNOTEL observations and modeled basin snow water resources over time. Lastly, one of the main goals of the snow modeling we're doing is to try to aid the hydrologic model that we're developing for this project through calibration and also representation of snow processes. So I'm going to pass it over to Colin Penn, and he's going to talk about some of the hydrologic modeling.
All right, thanks, Graham. So the USGS has a surface water model called the Precipitation-Runoff modeling system. They've developed a national hydrologic model, which is across the conterminous U.S. and parts of Alaska, where they've kind of pre-processed a lot of these basin parameter sets by HRU, and you can pull out specific areas of the model. So for this, focusing in on the Rio Grande Headwaters, we have the Rio Grande Headwaters PRMS model, which is made up of 28 hydrologic response units. These are shown in pink. And these are based on points of interest within the basin, such as gauges, like the Del Norte gauge, major confluences, and then also elevation. So you see some higher elevation HRUs in the high elevation regions of the model. The model, as part of this national hydrologic model, is regionally calibrated, but as you can imagine, regionally calibrating for the whole Rio Grande might miss some of the measurement marks that we'd want to hit in the headwater areas. So using the National Hydrologic Model pull as a baseline, we did a further calibration using the DayMet forcing product from 1980 to 2015, and that kind of incorporates some of those climatic changes that the previous presentation highlighted. We used the program LUCA to calibrate by basin and subbasin for a 10-year period, focusing on these processes of runoff, snow melt, soil moisture, and evapotranspiration, which were identified as some of the more sensitive processes in the basin. And you can see some of the fit parameters following that calibration. And then a baseline run using PRMS was run from 1990 to 2015, kind of this, the forecast region or area that we're focusing on for the period of record. And so some of the results from PRMS and compared to the water supply outlooks, overall, annually, you can see that the model has a pretty good fit to gauged observations, fairly high Nash Sutcliffe and volumetric efficiency metric. Bless you. When we compare this to the water supply outlooks, you can see that the range of PRMS simulated flow is much more constrained than the water supply outlook. So when you compare maybe the whole period of record, the overall bias is similar magnitude, but you can see this high and low in the water supply outlook is constrained to a much more smaller range in the PRMS simulated flows. And this is kind of highlighting that forcing data is incorporating those climatic changes in this is minimum and maximum temperature from that DayMet forcing product. You can also see that the PRMS model is much more consistent in its bias, so a consistent over-prediction up until about 2006 when it switched to this under-prediction period, and that may or may not be related to the bark beetle epidemic in that area. And so to incorporate bark beetle into PRMS, we manipulated the vegetation parameters, specifically the summer and winter cover density, and then those in turn impact the radiation transmission to the canopy and the snow and rain interception parameters within PRMS. And so we used the cumulative mortality time series from the Forest Service that David showed earlier in the presentation to modify the cover density within each HRU, and then use that modified cover density to calculate a new radiation and intercept parameter for PRMS by each HRU. And some of the new features of PRMS include a dynamic parameter scheme which allows you to change these through time without having to stop and restart your modeling scheme. So the big question is, how much did this bark beetle impact runoff within the basin from a modeling standpoint? Well, you can see in this in the simulated and observed flow plot in the top that there's not a huge difference between the baseline simulation and the bark beetle simulation. And this is actually kind of expected. Previous literature has shown that the difference at a basin scale, the difference in flow is about 10% more in bark beetle impacted area compared to sort of unimpacted or unaffected areas either from a numerical modeling standpoint or from a comparison to historic and current flows. There's several studies that have looked into that. And then when you look at the impact on the percent bias, you can see that reflected in years where the baseline model was over-predicting. That increased flow bumped that bias up by a measurable amount. And then in the areas where the model was systematically under-predicting, you can see that increased flow actually increased or reduced the bias in the bark beetle impacted model. But overall, not a huge difference attributed to the bark beetle. And so the next thing we're looking at is the fire impacts. You can see at those last 3 years, the 2013 fire, both the water supply outlook and PRMS models show systematic under-prediction in flow through that period. Another thing to point out is there's these years where overall the water supply outlook and bias in the PRMS model are pretty consistent in their, at least in the direction of their bias, but there's these several years where they deviate, and so we're sort of starting to look into that and what reasons or what factors might be causing that deviation. And so our next steps with this project, like Graham mentioned, we're kind of in the middle of it right now. Our next step is to incorporate these fire effects into PRMS and compute and compare them to baseline results in the water supply outlooks. Then compare the PRMS and snow model, snow output, and see if we can improve the snow scheme in PRMS to better represent snow throughout the whole basin, and then use our physical models and the water supply outlooks to see if there's a, like Graham mentioned, a relationship that changes through time between SNOTEL and basin-wide snow water equivalent, and then see if we can improve that the snow and runoff ratio for future water supply forecasts based on any observations that we see. And finally, in addition to the climatic effects that the previous presentation highlighted, we're going to look at some sort of other factors that may be affecting snowmelt in the area, such as dust on snow and other things like that. So that's the end of our presentation. I guess we'll pass it back to Mike, and we'll open it up for questions.
Hey, great presentation, guys. This is John Bumgarner from the New Mexico Water Science Center. For your model calibration, did you guys do a calibration for the entire study period, or did you do a calibration for pre and post bark beetle infestation?
The calibration was from 1980 to 1990, so pre-beetle.
Pre-beetle, okay, thanks.
This is Tim Kirkpatrick with New Mexico Prescribed Fire Council. Have you done a correlation for prevailing wind and wind temperature? I seem to recall that during some of these periods where you show a discrepancy, we had an unusual shift of warm winds out of the southwest compared to what would be a consistent normal of wind out of the northwest.
Yeah. No, we haven't looked into that, but that's, really great advice on, we're definitely, wanting to take it further and try to dig into, specifics in these years and what, climatic factors or other factors may have been, influencing these errors. So, we appreciate that advice.
I have one question on the first presentation. The temperature trend is increasing starting from 97.3 up to present. But if we go back before 97.3, it's also increased the same kind of trend that we have. So I don't know how can we say that there is a temperature increase, 3 degrees centigrade, something like that, on the graph. So we have to include, I think, both before 1973 and after 1973.
So it looks like David's not, either he's been muted or he can't hear us. What I can do is I can take your question down, and I can go ahead and email him and make sure you get a response.
Okay. I have also another question for the last presentation.
Okay.
So when you really use the hydrologic model for land use for the forest, did you consider different types of forest like deciduous forest, mixed forest, or evergreen forest in your model?
Yeah.
You know what would be?
Oh.
Go ahead.
The PRMS model kind of has 4 different land cover schemes, and so the dominant one is what makes up the sort of cover type for each HRU. And so there is an evergreen HRU type, and then there is a mixed forest HRU, vegetation type that you can specify for each HRU. And so it is differentiated between the 2.
So you have like evergreen, mixed, and deciduous forest, or just only evergreen and deciduous, no mixed?
Correct.
Mixed.
No mixed, just evergreen or deciduous. But you can set the transpiration beginning and end period. And so for an evergreen forest, you can set a deciduous scheme, and then the cover density won't decrease significantly between the summer and winter months. And so you're essentially representing an evergreen forest with a mixed forest scheme.
Thanks.
Yep.
Okay, are those all our questions? Okay, everyone, it looks like I don't see Mike anymore, so we can go ahead and wrap this up since it's already after 5, so thank you so much to the presenters. And if no one has anything else to say, we can go ahead and close this up.
Thanks, everybody, for attending.
Thank you, everybody.